Welcome to Học Tiếng Anh với Joseph, where we build vocabulary and practice pronunciation through reading. Continuing with The Cat in the Box, today we will read story number 68. Hôm nay chúng ta sẽ đọc câu chuyện số 68, Electron Waves and Quantum Duality. During the 1920s, a combination of theory and experiment led to a dramatic advance in our understanding of the world of the very small, atoms and below, in the form of quantum mechanics. The best example is the discovery that electrons are both particle and wave. Albert Einstein's explanation of the photoelectric effects had led to the identification of a simple equation relating the wavelength of a particle color of light to the momentum of the particle of light with that color. Wavelength is, of course, a property of waves. Momentum is a property of particles. Light seemed to be both wave and particle, but at first, this looked like a peculiarity of light alone. Then, in 1924, in his PhD thesis, the French physicist Louis de Broglie put forward the idea that Einstein's equation could be turned around to give a wavelength of any particle in terms of its momentum. In particular, this implied that electrons should behave like waves under certain circumstances. The key equation is lambda equal h over p, where lambda is wavelength, p is momentum, and h is a very small number known as Planck's constant. Because h is so small, the wave-particle duality is predicted to show up for only tiny objects, the size of atoms or smaller. Even before the Broglies published his idea, Clinton Davison, an experimenter at the Bell Laboratories in America, had been studying the way electrons bounced off or scattered from a nickel surface. On a visit to Britain in 1926, he was astonished to hear the German theorist Max Born give a lecture in which he quoted some of Davison's published results as supporting the Broglies' idea. Back in the USA, late in 1926, he set out with his assistant Lester Gummer to make a proper test, using essentially the same techniques that the Braggs had used to study X-rays. In the American experiment, which produced results early in 1927, electrons from a hot wire were accelerated by electric fields and fired in a beam at a nickel surface. This target could be rotated to different angles, and the electron detector used to monitor the scattered electrons could also be moved to different places to observe the electrons coming back from the surface. They found distinct peaks in the intensity of the scattered electron beam at certain angles, exactly matching Bragg's law for waves diffracted by the atoms spaced out in the crystal lattice. The wavelength implied was exactly the wavelength obtained from the Broglies' calculation. Meanwhile, the British physicist George Thomson, the son of J.J. Thomson, based in Aberdeen, had also heard Born's lecture and set out to search for evidence of electron waves by firing electrons through thin pieces of gold foil between 1/10,000th and 100,000th of a millimeter thick in a cathode ray tube. Early in 1927, he produced a diffraction pattern on photographic plates and proved that it was caused by electrons, not X-rays, by bending the beam with electric and magnetic fields. It agreed with the predictions from de Broglie's calculations to within 1%. Two subtly different experiments had almost simultaneously proved that de Broglie's was right, or as Davidson put it in his Nobel lecture, that streams of electrons possess the properties of beams of waves was discovered early in 1927 in a large industrial laboratory in the midst of a great city and in a small university laboratory overlooking a cold and desolate sea. Discoveries in physics are made when the time for making them is ripe and not before. Davidson and Thomson shared the Nobel Prize in Physics in 1937 for their experimental discovery of the diffraction of electrons by the crystals. De Broglie had already received the prize in 1929 for his discovery of the wave nature of electrons, but physicists were left struggling to understand how subatomic entities could be both particle and wave. In the course of this struggle, they developed two different versions of quantum mechanics. One, essentially based on the particle idea, was developed by Werner Heisenberg and his colleagues. The other version, based on the wave idea, was developed by Erwin Schrödinger. The two theories are mathematically equivalent, and they are both good theories because they each give the right answers to calculations involving the behavior of things like electrons when compared with experiments. But it remains a mystery how the world can be like that. J.J. Thomson was awarded the Nobel Prize for proving electrons are particles. His son was awarded the Nobel Prize for proving electrons are waves. Both are right. Don't worry if you cannot see how this is possible. As another Nobel Prize winner, Richard Feynman, used to say, nobody understands quantum mechanics. Moving on to the vocabulary section. Dramatic, drama, dramatic. Quantum mechanics. Identification. Identify, the verb. Momentum. Momentum. Peculiarity. Peculiar. Peculiarity. Scatter. Scatter. Astonish. Astonish. Essentially. Essential. Essentially. Desolate. Desolate. Not desolate. Desolate. Struggling to understand. Struggle, struggling, struggling to understand. Equivalent, equal, equivalent. Thank you very much for your time. And as usual, I will see you in the next story. Bye for now.